Hi everyone. So last time we learned that we can sometimes describe curves in polar coordinates. And in nice cases, the equation can be expressed in a form where r is just a function of theta. So here are a couple of examples. There's r equals theta, which looks like a spiral. And then there's r equals 2 minus 2 sine theta, which looks like a heart. Math is so nice, isn't it? So anyway, in today's lecture, we're going to learn how to do some calculus involving curves in polar coordinates. So one thing that calculus is useful for is calculating areas. So here's a question. Suppose we have a curve that's expressed in this form, r equals f of theta. What is the area inside the curve between two given theta values? And so here's a picture where the bounds for theta are theta equals a and b. And we can look at the area that's inside the curve as you go from theta equals a to theta equals b. So how do you calculate that area? Well, let's start with the simplest case, where r is constant. And of course, in that case, the curve is just a circle. And then instead of using theta equals a and theta equals b, it's going to be convenient for us to use delta theta to represent that internal angle for the area that we're calculating. Okay, so one thing we know about this is that the area of the whole circle is pi r squared. And another thing that we know is that the fraction of the circle that is shaded is delta theta over 2 pi. And that's because the whole circle would be when delta theta is equal to 2 pi. If delta theta was equal to pi, then that would be half the circle, and so on. And so in general, the fraction of the circle that is shaded is delta theta over 2 pi. And so then putting these two facts together, we conclude that the area of the shaded region is pi r squared times delta theta over 2 pi. And then the pi's cancel, so the formula can just be written as r squared over 2 times delta theta. All right, so now that we've figured out how it works when r is constant, we're ready to move on to the general case. And the way that works is that if delta theta is small, then you can approximate the area by a slice of a circle. A good way to think of it is that we're using these circular slices to approximate area in polar coordinates exactly the same way that we use rectangles to approximate areas in Cartesian coordinates. And so we have this approximation of the area as r squared over 2 times delta theta, and that approximation gets better and better as delta theta goes to 0. And in the limit, we obtain an integral. And so we end up with the formula that the area inside the curve is the integral from a to b of r squared over 2 times delta theta. And just to clarify and emphasize, in this context, r is a function of theta, and so you need to remember to plug that in before you calculate the integral. So let's look at an example. Consider the function r equals sine of 2 theta. And if you graph it, you get this cute little flower. And actually, I'm going to give you an exercise, which is to figure out how the petals of the flower get traced out as theta goes from 0 to 2 pi. But the question that we'll answer right now is, what is the area in one petal of the flower? So the first thing to think about is, what is the theta range that covers that part of the curve? And of course, that's related to the exercise I gave you, but I think you can sort of see that the first petal gets traced out as theta goes from 0 to pi over 2. As theta goes from 0 to pi over 2, sine of 2 theta will go from 0 to 1 and then back down to 0 again. And that gives you one full petal of the flower. And now we just need to use this area formula. The area is the integral from 0 to pi over 2 of r squared over 2 d theta, and then we plug in r equals sine of 2 theta into that. And now this integral, it's possible to do it by hand, but it isn't fun, so I'll just tell you what the answer is. And the answer, according to Wolfram alpha, is pi over 8, and so that is the area in one petal of the flower. All right, so what else can we do with calculus? Well, one thing we do is we take derivatives and calculate slopes. And so the question is, if we're given a curve of the form r equals f of theta, how do we find the slope at any point on that curve? And it should be pointed out that f prime of theta is not the answer. F prime of theta is the change in r over the change in theta. It's not change in y over change in x, and that's really what we want when we're talking about the slope. But it turns out that there's a simple trick that allows us to answer this question. Remember that we have these formulas, x equals r cosine theta, y equals r sine theta, that relate the Cartesian coordinates to the polar coordinates. So if we have this equation for the curve, y equals f of theta, we can substitute that in so that we can express x and y purely in terms of theta. And we can interpret those equations as being parametric equations for x and y as a function of theta. So theta is the parameter. And that means that we can use the formula that we already know for the slope of a parametric curve. And that formula in this case is dy dx is dy d theta over dx d theta. So here's an example. What's the slope of the curve r equals sine of 2 theta at theta equals pi over 4? So in this case, sine of 2 theta is the f of theta in the above formula. And so that means that x is sine of 2 theta times cosine of theta, and y is sine of 2 theta times sine of theta. And then we can calculate dx d theta, and there's a product rule there, but otherwise it's straightforward. And then the question is asking about theta equals pi over 4, and so we'll plug that in. And when you do that, cosine of 2 theta becomes cosine of pi over 2, which is 0, so that term goes away. Sine of 2 theta becomes 1, and sine of theta is square root of 2 over 2, so the result is minus square root of 2 over 2. And then similarly, we can calculate dy d theta. And again, we plug in theta equals pi over 4, and the first term goes to 0, and the second term becomes positive square root of 2 over 2. And so then we finally get that dy dx is square root of 2 over 2 divided by minus square root of 2 over 2, and so you get minus 1. But I'll point out that this calculation of the slope was really just an application of this really more powerful idea, which is that you can get parametric equations from a polar equation. And once you do that, then you can do anything that you do with parametric equations, you can do with the polar equation. So for example, you could calculate arc length. And there's really nothing new that I need to teach you here, because it's really just a matter of plugging in these equations for x and y into the formulas that you already know for calculating the arc length of a parametric curve. So there's a problem in the worksheets that asks you to do that, but you're ready for it already, I promise.